So today we'll discuss we have to review the vector spaces, subspace with examples and spanning of sets, linear independence, basis and dimensions, applications of vector space and related theorems. First of all, what is linear combinations? We can add and scalar multiply in the same equation. Suppose W equals to C1 B1, C2 B2 plus dot dot plus CP BP, where C1 C2 dot dot CP are scalars and B1 B2 dot dot up to BP are vectors in Rn. That means n-dimensional space, and W is a vector in Rn. So the scalars belongs to real numbers in n space, and W are the vector in n space. So the definition of linear combinations, we call W is a linear combination of the vectors B1, B2, BP. The scalars C1, C2 up to CP are called weights or coefficients. So for example, we can give an example of linear combinations. Suppose B equals to the vectors 1, 2 and W equals to 1, 0. So 1 is the value of x-axis and 2 is the value of y-axis. Okay, y values. Similarly in W space. Suppose in coordinate system, what are some linear combinations of B and W? Suppose if you add B plus W, we get 2, 2, 2. Okay, so B plus W is this is the point, this point. I am highlighting this point. So we can, so this is the point. This is the point. Okay, this is the point B plus W. Similarly, B minus W, what? B minus W means 0, 2. So 0, 2, 0, 2 is this. That means x value 0 and y value x value 2 and y value 0. So this is why these values x value 0 and y value 0. This one is the B minus W. Okay. Similarly, twice B plus 0W, what will be the values? Twice B 2, 4. Okay. So 2, 4. 2, 4 means x value 2 and 4 value what? This one. So this one is the twice B plus 0W. Similarly, another linear combination, twice W what? Twice W, 2W. That means 2, 0. So 2, 0 means what? X value 0 and this is the 2. So this means what? This means 2W. And minus B what? Minus 1, minus 2. Minus 1 means this, minus 1 and this minus 2. So this is the actually minus 1, minus 2. And this is the example of linear combination of two vectors B1, 2. So this is the examples of linear combinations of B and W. W are the vectors along x-axis this, and B is the vector this. For what? This one. Now, so in fact, is there any vector in R2 that is not linear combination of B and W? So in that case, what can we do? In fact, every vector in R2 is a linear combination of BW. This is the W vector and this is the B vector. So the purple lines are to help to measure how much of B and W you need to get a given point. So another more example. What are some linear combinations of B to 1? So this is the thrice 3 by 2 B and minus half B and this. Actually, this is the B vector and this colored line are these values. What are all linear combinations of B? All vectors CB, that means C is a real number. C means what? 3 by 2 minus half, etc. are all scalar multiplied with B. These form a line. This is why we can write as a linear combination. Now another question arises, what are what are all linear combinations of B and W? Answer, the line which contains both vectors. The line which contains both vectors is called linear combination. So what's the difference between this example and the one on the board? So this is the example of linear combinations and definitions also. Okay. Now another one, span. What is the span? It is important to know what are all linear combinations of set of vectors b1, b2 up to bp in Rn space. It's exactly the collection of all b in Rn such that vector equation can be written as this: x1 b1 x2 b2 plus dot dot xp bp equals to b, where x1 x2 dot dot x all x are belongs to what? Real numbers, scalars, and b1 b2 bp up to bp are vectors and has a solution that is consistent. Now we can define the span of vectors. So definition, what will be? The let b1 b2 dot dot bp are the vectors in Rn. The span of b1 b2, that means span of these vectors, is the collection of all linear combinations of b1 b2 up to bp and is denoted by a span b. In symbol, we can write a span of this set of vectors equals to, we can write all the linear combinations x1 b1 plus x2 b2 dot dot plus up to xp bp such that all x are in real number. So this sets, this is the set, okay, and this is the such that. So synonyms of span of these vectors is the subset of a span by or generated by the vectors b1 b2 dot dot up to b. So this is the first of several definition in this class we can simply must learn. Now the span can be explained as, so in several equivalence, a vector b is in the span of b1 b2 dot dot up to bp, and the vector equation can be written as like this, has a solution. The linear system with argument vector, argument matrix is consistent, that means it will have solutions. Now this is the picture in an inconsistent linear system. Now watch the picture of spans. So drawing a picture of a span of vector b1 b2 dot dot up to bp is the same as drawing a picture of linear combinations of these. Suppose b is the vectors with red line, but the span of b, all the linear combinations of these vectors, this whole line is the span of b. And similarly, a span of bw will be, this is the red line b vectors, and w is the green. So this span of bw. Similarly, a span of bw can be written as like also this. This is the b vectors and this is the w vectors. So span of two vectors in R2 space, that means in two-dimensional space. Similarly, picture of span in R3 space. This is the three-dimensional space. This is the only single vector b, and span of bw in 3 space will be like this. And similarly, ubw in three-dimensional space. This is the u and this is the b and this is the w. So a span of ubw can be imagined as like this. This is the span of bw. That means these three vectors are can be expressed as linear combination of the set of vectors. So this is the span of two vectors in R3 space and span of three vectors in R3 space. Now, how many vectors are in a span? These zero vectors, 0, 1, infinity. In general, it appears that span of these vectors b1, b2 dot dot bp is the smallest linear space. That means line, plane, etc. Linear space containing the origin and all of the vectors of this. I will make the precise later. So summary, The whole lecture points vectors and linear combinations span of vectors. Now we'll discuss the linear independency of vectors. So the linear independency of vectors in this connection, sometimes the span of set of vectors is smaller than you expect from the number of vectors. Actually, this is the span of BW, and this is the span of three vectors in R3 space. And this means that at least one of the vectors is redundant. You're using too many vectors to describe the span. So actually, what's the definition of linear independence? The definition, a set of vectors b1, b2, dot, dot, up to bp in Rn space is linearly independent if the vectors equation, that means linear combination, equals to 0, has only the trivial solution like this. All scalars are 0. x1, x2 equal to x2 equals to all xp equals to 0. Then the set of vectors is called linearly independent vectors. In other words, b1, b2, dot, dot, up to bp set of vectors is linearly dependent if there exist number of scalars x1, x2, dot, xp not all equal to 0, such that this linear combination equals to 0. And this is called linearly dependence relation or equation of linearly dependence or linearly dependence of vectors b1, b2 up to bp. Now, the definition can be called also the set of vectors b1, b2 up to bp is linearly independent of the vectors. This has only trivial solution. The set is linearly dependent otherwise. Okay. So note that in linear dependence is a notation that applies to a collection of vectors, not to a single vectors or to one vector in the presence of some other words. Now checking the linear independency, is the three vectors linearly independent? Equivalently does the homogeneous vectors equation. We can write the linear combination where x is the scalars, y also scalars, and z is the also scalars. This is the linear combination of 0 equal to 0. Have a non-trivial solution. How do you solve the kind of vectors? Suppose this is the matrix form 1, 1, 1, first row, second row, and third row. So row redundancy, making first row, this is the row reduction, just subtracting, we get this one. Okay, here we obviously get x equals to what? Minus 2z and y equals to minus z. So the vectors are linearly dependent because one scalar, that means is 0. And an equation of linearly dependence taking z equals to 1, we get minus 2, this one. Just if z equals to 1, then x equals to minus 2 and y equals to minus 1 and z equals to 1. So this linear combination can be expressed as like this. So we obviously say that this is linearly dependent because all scalars are non-zero. Now another one, this is the linearly independence checking. Now suppose these three vectors, and we can write the linear combination with the scalars x, y, z equal to 0. Now this matrix can be reduced to this. For solving, that means by Echelian form, we can write this one, just making first row, third row x, y, 0, and second row x, 0. So we get the trivial solution x equals to y equals to 0. This is the all scalars are 0. So the vectors are linearly independent. So because these three scalars are 0. If all scalars are 0, then the vectors are said to be linearly independent. But the previous examples, all scalars are not 0. This is why linearly dependent. Now the linearly independence in R2 space, the vectors in span of B can be written as like this. So one vector B linearly independent if B is not equal to 0. So linearly independence is R2 space, span of W, one vector B linearly independent if B is not equal to 0, and two vectors BW linearly independent if neither n is in the span of the other and span got bigger. That means the span of W is this and span of B this. Okay. So these two vectors span of BW linearly independent. Similarly, the one vector B and linearly independent if B is not equal to 0, and two vectors BW linearly independent, neither is the span of the other and a span got bigger. Three vectors, similarly, we can say that linearly dependent if U is in the span of BW, U is in the span of BW, and a span did not get bigger after adding U, can remove U without shrinking the span. So B is in the span, B is the span UW, and W is in the span, W is in the span what? UB. So in this case, two collinear vectors BW linearly dependent if W is the span of B. And that means W and B combinedly linearly make a linear combination. Can remove W without shrinking the span. Span did not get bigger when we added W. So two vectors are linearly dependent if and only if they are collinear. Collinear means what? Say in the both vectors exist in same line or same vectors. Similarly, in R2 space, the three vectors BWU linearly dependent if W is a span of what? BW, BU, and can remove W without shrinking the span. Span did not get bigger when we add W. And if a set of vectors is linearly dependent, then so is a larger set of vectors. Now, the linear independence in R3 space, that means a span of B here and a span of W. Two vectors BW linearly independent, neither is the span of the other. Span got bigger when we added W. So W is the linearly independence. Three vectors BWU linearly independent for 3 space. So in three vectors BWU linearly independent, span got bigger when we added U. So this is the span of W and this is the span of B and this is the span of BW, B and W. Now span of BW, three vectors BWX linearly dependent if X is in a span of BW, can remove X without shrinking the span, and span did not get bigger when we added X. So this is the example of linearly dependent on three vectors. Now linear dependence and three vectors. Now, what are the subspaces? Actually, we are reviewing the vector spaces. In our previous lecture, we have discussed more about subspace and vector space. Now, today we'll discuss subspace of IR in an space. A subspace turns out to be the same as a span XC, except we don't know which vectors is the span of B. This arises naturally when you have, say, a plane through the origin in R3 space, which is not defined as a plane, but you still want to say something about it. This is the actually plane X plus 3y plus z equals to z. Now, what will be the definition of subspace? A subspace of a space is a subset of vector space B of Rn satisfying three conditions. First of all, the zero vectors is in B. If U and B are in B, then the sum of these two element of B also lies in B. If U is in B and scalar C is in R, then the scalar multiplication will exist in B. That means first condition is called not empty, zero vectors, and closed under addition and closed under scalar multiplication. If the vectors subset, if any subset of vector space B satisfies these three conditions, is called subspace. Every subspace is a span and every span is a subspace. Okay, so the definition can be draw the attention like this. So not empty condition, second condition closed under addition, and third condition closed under scalar multiplication. What does this mean? If B, small b is in capital B, then all scalar multiples of B sets in B by three conditions. So this is the line through B is in B. If UB are the elements of B, then scalar multiplication of XU and YB are in B for scalars, for any scalars XY in through two dimension. So the closed under addition will be lies in B. Likewise, if B1, B2 dot dot Bn are all the vectors in capital B, the span of is contained in B. A subspace contains the space of any set of the vectors in it. Now, example of subspace. Suppose a line L through the origin. This is the line through the origin. This contains the span of all any vectors in L. That means all the lines through joining through this L will be the span. For example, a plane P, suppose this is the plane P through the origin, and this contain the span of any vectors in P. Okay, so this L lies in whole in P. This is why the span of any vectors in P. Now, another example, all the real numbers in a space, this contains the origin 0 and is closed under addition and scalar multiplication. For example, the subset 0 vector, 0, this is the subspace contains only one vector. Note this, not all the pictures of spans, line, planes, spaces, etc. Now, subsets and subspaces. They aren't the same thing actually. Subsets and subspace are different thing. A subset of Rn is any collection of vectors, whatever. All of the following non-examples are still subsets. A subspace is a special kind of subset which satisfies three defining properties. This is the difference between subset and subspaces. And this is the actually subset, yes, but subspace, no. Now, non-example, a line L, this is the line L, or any other set that does not contain the origin is not a subspace because it does not satisfy the first condition of subspace. Non-example, a circle C is not a subspace because a circle is not a linear space. That means there is not possible close under addition. Non-example, the first quadrant in R2 space is not a subspace because fails 3 only. That means 3 what? The third condition, scalar multiplication, is not possible here because this is the only defined in only first quadrant. Suppose scalar multiplication -1, -2, etc. Will be another quadrant. This is why first quadrant in R2 is not a subspace. A line union a plane in R3 is not a subspace because closed under addition or multiplication is not possible. That means closure law fails. Now spans are subspaces. If B is a equals to the span of this, we can say that B is a subspace generated by or spanned by the vectors B1, B2 dot dot Bn. Suppose 0 can be written as like this linear combination of B1, B2, B dot dot Bn is the span. If say U equals to this and B equals to this, then U plus B sum what will be this. So it's also a span because it can be written as U plus B can be written as linear combination of two vectors. Similarly, if U is the span, then so scalar multiplication for any scalar C also satisfy the properties. So now we have to verify what are the subspaces. Let B equals to AB set AB vectors in R2 space where AB is equal to 0. Let's check the B is a subspace or not. Does B contains the 0 vector? Suppose the vectors AB equals to 0, 0, then implies AB equals to 0. That means first condition satisfied. Now, 3 condition, if B is closed under a scalar multiplication, let AB be in B. This means that A and B are numbers such that AB equals to 0. Let C be any scalar seen to the vector AB equals to can be written as CB, which is exist in B. This means that scalar multiplication equals to 0. We call that also CA and CB equals to C square AB, that means 0. That means closed under closure law satisfied. Close under addition. Now B is closed under addition. Let A be closed under scalar multiplication. Now second laws, verifying second law is B is closed under addition. Let A B and A dash B dash are two unknown vectors which lies in B. This means that A B equals to 0 and A dash B dash equals to also 0. And so this sum of two vectors can be written as this, which is also lie in B. This means that a plus a dash into B plus B dash also 0. So this is not true for all such vectors a dash B B dash. For instance, 1 0 and 0 1 are in B, but their sum 1 1 is not in B because 1 into 1 is not equal to 0. So we conclude that B is not a subspace because second condition, that means vector B is not closed under addition. It does not look like the span. Now column space and null space. Suppose M cross N matrix naturally gives rise to subspaces. Definition: the column space of A is the subspace of Rm spanned by the column A. It is written as column space. The null space of A is the set of all solutions of the homogeneous equation X equals to 0, and null space A equals to can be written as X in Rn such that X the homogeneous equation. This is the subspace of Rn. The column space is defined as the span, so we know that it is also a subspace. Now check the null space is a subspace. 0 is the null space of A because A into 0 equals to 0. That means first condition satisfied. If U and B are in null space of A, that means scalar multiplication A equals to 0 and A equals to 0. Hence, this equals to 0. So U plus B is in B, null of A. That means second condition satisfied. Number 3, if U is the null space of A and scalar multiplication of U equals to 0 for any scalar C, we can write this one 0. That means CU is a null space of A. So this vector satisfies all the properties of subspace. This is why all null space are subspace. Now column space and null space, let any two matrix with 2 column and 3 rows. Let's compute the column space. Column space of A equals to span of these two vectors. Now span of 1 1 can be written as like this, which is the straight line in R3. Let's compute the null space. The reduced row echelon form of A is this. Now this gives equation x plus y equals to 0 and x equals to minus y. That means x equals to y. Parametric vectors will be like this. So hence the null space is span. This is a line in R2 space. The null space is a span. The column space of a matrix A is defined to be a span. The null space is defined to be the solution of this. So, and it is a subspace, so it is a span. Now question arises, how to find vectors which span the null space? The parametric vector form, we know that the solution of homogeneous equation x equals to 0 has a parametric form look like this. So if we say x3 and x4 are the free variables, so null space of A can be written as this 1 2 1 0 minus 2 3 0 1. Now, what are the basis and dimension? So in subspace, we have discussed a subspace of Rn is the same thing as a span, except we haven't computed the spanning set. For example, column space of A, null space of A for a matrix A, there are lots of choice of spanning sets of a given subspace, or some better than others. Now, basis of a subspace. What are the smallest number of vectors that are needed to be a span of a subspace? Smallest number of vectors that are needed to span of a subspace is called actually basis. Now definition, let B be a subspace of Rn. A basis B is the set of vectors in B such that B can be a span of this, that means can be written as a linear combinations. And B1, B2 dot dot Bm are linearly independent vectors. So in our previous slide, we have discussed what are the linearly independent vectors. So if any subspace satisfies these two conditions, is called the basis. The number of vectors in a basis is the dimension of B and can be written as dim B. So why is the basis? Why is a basis the smallest number of vectors needed to span? Now we can verify some example. Now basis of R2. What is the basis for R2? R2 space. We need two vectors that span R2 and are linearly independent. E1 and E2 is one basis. Suppose this is the E1 and this is the E2. So these two vectors can be written as a linear combination with some scalars AB. Okay, and they are linearly independent because they are not collinear. Linearly independent, why? That means the two vectors don't pass through in the same line. That means they contain the the content in different direction. This is not in same direction or opposite direction, or not lies in a line. This is why they are linearly independent. Now, what is another basis for R2? Any two non-zero vectors that are not collinear. Suppose this is the 1 0 vector and this is the 1 1 vectors. Okay, that means x equals to 1 and y equals to 1 here, and this is the x equals to 1 and y equals to 0. So for this example, 1 0 and 1 1 is also a basis. The span has a pivot in a row, every row. They are linearly independent, has a pivot in every column. This means in this case this is also a. Now basis of Rn. Suppose the unit coordinate vectors e1 1 0 0 and e2 0 1 0 0 dot dot en minus one term 0 0 1 0 and last term will be 0 0 dot dot 1. This is the standard basis of n space as the basis of Rn. Now the span, that means in has a pivot in every row and they are linearly independent. In has a pivot in every column. In general, the vectors b1 dot dot bn is a basis for Rn if and only if the matrix A has a pivot in every row and every column. That means can be written as a linear combinations. Now, for example, basis of a subspace. For example, B equals to xyz in R3 space where the plane x plus thrice y plus z equals to 0 and B equals to minus 3 1 0 and 0 1 minus 3. The verify that B is a basis for B. So dimension of B equals to what will be 2. Okay, because two vectors. It is a plane. Now, first of all, in B, both vectors are in B because this can be written as x equals to what? Minus 3 and y equals to 1 and z equals to 0 for the first equation. And for the second equation, x equals to 0, y equals to what? 3 into 1 and z equals to minus 3 equals to 0. That means we get the linear combination satisfied. Now with 0 vectors. Now span if xyz is in B, then y equals to what will be from the first equation, given equation minus 1 by 3 x plus z. So xyz can be written as minus x by 3 with first vector minus x by minus z by 3 with second vector. And linearly independence with two scalars c1 c2, we can write the c1 c2 equals to 0. That means every constant, every scalars are 0. This is why the two vectors are linearly independent, and these are the two bases. Now, what are the bases of a vector space? A subset S of a vector space B is said to be the basis of this if S contains linearly independent vectors and S generates the subset of a vector space generates the vector space B. That means B can be written as all the linear combinations. So each vector in B is a linear combination of a finite number of elements of S. Now, for example, a system of S containing n vectors e1, e2 dot dot up to en is a basis of this. Now, first we should show that S is a linearly independent set of vectors. We have proved it in the previous example. Now we should prove that LS equals to, that means all the linear combinations of vectors. And so let alpha equals to this be an any vectors in vector space. Then we can write a1 a2 dot dot n equals to a1 plus a2 second vector plus dot dot n nth vectors. That means alpha equals to a1 e1 plus a2 e2 plus dot dot n in. And S is the basis of this. We shall call this particular basis is a standard basis. This is called standard basis of vectors. For example, show that the following set is a basis for in R3 space. Suppose n1 s equals to 1 0 0 0 1 0 and 0 0 1 are the this is the geometrical figure for these three vectors. So S is linearly independent because the vectors can be written as a linear combinations and we can solve easily where C1 equals to C2 equals to C3 because all scalars are 0. This is why S is linearly independent vectors and S is the basis for R3 because S can be written as a linear combinations also. So the basis S equals to this is called the standard basis for R3 space. The result can be generalized in N space also. E1, E2 dot dot up to N space form the basis on Rn space, standard basis for Rn space. So now another example in R2 space, show that 1 1 and 1 minus 1 are the basis of R2. According to the definition of basis for a vector space, you must show that S spans R2. That means S is linearly independent. To verify this, S spans in R2 space, let x equals to x1, x2 vectors. This can be written as a linear combination of this x equals to c1 b1 and c2 b2, where c1 c2 are the scalars. Now b1 equals to first vector and b2 equals to 1 minus 1 second vector. So this can be written as this. Now equating corresponding components, we get first one equals to x1 and second one equals to x2. Now solving, adding and subtracting, we can find out the values of the scalars. So it has a unique solution. So we must conclude that S spans R2. To show that S is linearly independent vectors, consider this linear combination equals to 0 and C1 first vector, C2 second vector is 0 0. So solving, actually we get C1 equals to C2 equals to 0. So we can conclude that S is linearly independent. So we can conclude that S is the basis for R2 space because it is linearly independent spanning set of R2. Similarly, for R3 space, for example, proceeding in the same way, we can show that S is the linearly independent vectors. So S is also basis for R3 space. Now a basis for a polynomial show that the vectors space P3 has a basis 1x, x square, x cube. It is clear that S spans P3 because the span of S consists of all polynomials of the form not a1x plus a2x square plus a3x. That means linear combination of this given set S. Now not a1, a2 and a3 are real, that means scalars belongs to real number. So the polynomial, to verify this, we can write the linear combination equals to 0. Now after solving this is the third degree polynomial is said to be identical equal to 0. From algebra we know that polynomial to be identical equal to 0, that means n not equals to 1, all scalars will be 0. So S is linearly independent vectors. Now the basis S is called the standard basis for polynomial P3 polynomial. Similarly, the standard basis for Pn is this also. Now, another example, S is equals to these 4 vectors. That means M 2 cross 2 matrix is called a standard basis for M22. That means 2 root 2 column. In a similar manner, the standard basis for the vectors Mn, we can also conclude that it is also basis. Now, what are the dimension of a vector space? The definition: if a vector space B has a basis containing n vectors, then the number n is called the dimension of B, denoted by dimension of B equals to n. That means if B consists of the non-zero vectors alone, the dimension of B is defined as 0. Now, the definition allows us to observe the characteristics of dimension of the familiar vectors. Right, the dimension of n space with a standard operation is n. The dimension of polynomial nth degree polynomial standard basis will be n plus 1, and the dimension of M cross n matrix with the dimension operations Mn. So this is the we'll discuss now an example. Finding the dimension of a subspace. Determine the dimension of each subspace R3. That means W equals to DC minus DC, where C and D are the real numbers, and W equals to twice B, B0, where B is a real number. The goal in each example to find a set of linearly independent vectors that spans the subspace. Now, by writing the representation of this as this, okay, linear combinations. DC minus DC can be written as 0CC plus D minus D0. That means C00 C into 1 1. That means this. So you can see that W is spanned by the set these two sets. So using the technique describing the preceding section, we can show that this set is linearly independent vectors because these two sets can be written as a linear combination of two vectors with a scalar C and D. So it is a basis for W, and we can conclude that W is two-dimensional subspace. By writing the representation vectors 2b, b0 can be written as b into 0. That means a scalar multiplication with vectors 2, 1, 0. So you can observe that W is spanned by S 2, 1, 0. So W is one-dimensional subspace of R3. Now another one, find the dimension of the subspace W in R4 space. That means in 4 space, these 3 vectors b1, b2, b3. Although W is spanned by the set S, and S is not basis for W because S is a linearly dependent set, because B3 can be written as a linear combination of B1 and B2. B3 equals to 2B twice B1 minus B2. This means that W is spanned by the set only B1 and B2. Moreover, S1 is linearly dependent because neither vectors is a scalar multiple of the other. Okay, and you can conclude that the dimension of W is 2 because B1 and B2 spanned by B1 and B2. Now finding the dimension of a subspace with the matrix also, and the matrix can be written as a linear combination of with 3 scalars ABC. So S equals to this matrix, this and these sets. matrix of set of matrix spans W. So S can be written as a linearly